All right, the last thing that you want to be familiar with is the energy changes related to the quantum atom and the atomic spectra or light that's given off when you excite different elements. All right. So if you remember, we talked about this back with Bohr. He figured out that electrons near the nucleus have low energies, electrons far from the nucleus have high energies. We've got our ground state electrons, where all of these are electrons. This is the lowest possible energy. And then what do we call it when we energize or add extra energy into one of our electrons? That's when we get its excited state, and we actually cause the electron to jump up to a different orbital. All right? But this isn't permanent. All right? Electrons are eventually going to return to their ground state. Right? So they're going to temporarily get excited, have that extra energy, and then they're going to fall back down. And when they do that, they're going to give off energy. All right? They're going to give it off in the form of light. All right, so a couple of things related to this. You're not going to have to do calculations. You just need to be familiar with this equation. The energy released by an electron is equal to Planck's constant, which is just a value that makes the equation work. And it's a value that doesn't change. All right, so it's always 6.626 times 10 to the negative 34th joules seconds times the frequency of the light wave. All right, so the bigger the frequency, the more energy was given off. And related to that is you want to be able to compare different types of light waves to each other and describe what's going on in terms of their energy. All right? I don't know if you've ever really thought about this before, but there are types of light that we cannot see. All right? We can see the rainbow range, all right? Roy G. Biv. All right? But there is light above and below that energy-wise, right? So like the highest energy is going to be your gamma rays, right? Or you can also think of this as being highest frequency. Your lowest energy or your lowest frequency is going to be your radio waves. So using that sort of pattern that we have, all right, so as you go across this diagram from right to left, all right, energy is increasing. Using that idea, what color of visible light is highest energy? Hopefully you said violet, right? Because that's farthest over on this side. So this plays into this whole ground state versus excited state stuff, right? So electrons will jump given a certain amount of energy and then fall back down to their original state, right? When they fall back down, they give off light. What color light gives off can tell you how big the jump was. All right, so if you think about this, we've got a red jump, a green jump, and a violet jump. All right, we know red is low energy, violet is high energy, and you can see that the size of the jump varies based on the amount of energy of the light being given off. All right. So, a couple of questions that I want you to see if you can answer is what color light, so we're talking visible spectrum, what color has the least energy? And then, again, added a diagram to make this a little bit easier, but using this electromagnetic spectrum pattern, you should be able to answer both of these. So which color light has the least energy? And then which would be a bigger electron jump? One that releases microwaves or one that releases gamma rays? All right, so first one, which color light has the least energy? All right, you're going to focus on your Roy G. Biv range there. Hopefully you said red. All right. And then for which would be a bigger electron jump, one that releases microwaves or one that releases gamma rays? All right, you got to think about it. Is the jump bigger with high energy or with low energy? Now that you know that the jump is bigger with high energy, which of these choices is the higher energy? All right, we've got gamma rays here, microwaves there. So gamma rays would be given off when there's a bigger jump done by the electron.